Okay. So we're going to continue with probability today. Last class we were looking at how we added things together and putting different pieces together to find the ors and the ands. Today we're going to look at the multiplication rules and how we can find the probability of multiple events happening, which typically is what you see in most gaming type situations. So, and then we're also going to look at combinations and permutations, and I'm going to show you how to use the calculator to find those. You do not have to do those out by hand. All right, so the first thing we're going to look at is something known as conditional probability. So last class we were looking at how when two things were either mutually exclusive or they had overlap, we were able to figure those pieces out. Conditional probability looks at the probability that one event happens given something has already happened. So in this class, we looked at, I said we were doing males and wearing black, if I remember right from the last class. And we looked at how many people had those two situations or if there was overlap in it. Where the givens would be, I would say, what is the probability that given they're male, they are wearing black? So in that situation, I'm only going to be looking at the males as my bottom number because that's the given piece. So while this wonderful little thing down the bottom here looks really, really complicated, basically it's saying that you take the given part first, that is your bottom number. The top is the intersection between those two events happening. Once we do a problem, it'll make a lot more sense and a lot easier to see. So this little bar symbol right here, that means given. So it's the probability of A given B. And then remember that is just the intersection. Yeah. Thank you. All right, so let's look at this one. So we had a table like this last class. So it says we want to find, well, actually, let's look at it like we did last class. What's the probability that a person is 18 to 34 years old and likes the product? So what's the probability that they're 18 to 34 and they like the product? What's it as a fraction? Forget the actual decimal. What's it as a fraction? 200, wait, 213, right? Yeah. Okay. But it would be over the total. So in this case, it'd be 213 over the 1403. You're one step ahead of me because that's the next piece. So we were looking at it as it was out of the entire total. So we wanted that piece right there, and it was out of that total part down the bottom. Okay, that's what we did last class. The other thing we did was we're like, okay, well, what is the probability that they're 18 to 34 years old or they like the class? So in that situation, we're looking at all those and all those. Now, this was a situation where, okay, well, if we add up the 513 and the 550, because they totaled them already for me, I have to subtract out that 213 because I counted it twice. Okay? So those are the two situations that we did last class. Now, what you were saying was, what is the probability that they like the product given they are 18 to 34 years old? So in that situation, we're still looking at the 213, but since I said we gave you the fact that they were 18 to 34, this is the 213 over the 513. So that would be 18 to 30, or liked, given they're 18 to 34. All right, so that given piece tells you what the bottom is. Okay, because we pull that out first. We're like, okay, I know this is for a fact. Now, what's the probability they like the product? Does that make sense? All right, so if an individual is between 35 and 50, what is the probability that he or she will like the product? Yeah. Almost. 193 is correct. We gave you the fact that they're between 35 and 50. So that means we're going to be looking at that number there.
Oh, I misheard you.
That's okay. Yeah, if we know that the person's between 35 and 50, we're taking the 444, so that's the bottom. And in this case, they liked was the 193. All right, one more. Change my color again so I have the 3 different ones. So if we're given that they're not liked, what is the probability that they are over 50? I'll give everybody a second. So given that they are not liked, what is the probability that they are over 50? So what's the bottom number? Yeah. Okay, go say the whole thing then. Yes. So the bottom is where we're given. The bottom is not liked, which in this case is 600. And then the top is over 50, which is the 219. Yes.
Why would you choose the 600 over your 430?
What was the given piece? And it actually could go either direction depending on what we gave you first. So in this case, I said we're given that the person doesn't like the product. That's the assumption at the beginning. And then I said, okay, what's the probability that they're over 50? The other two situations, I said, given that the person's between 35 and 50, what's the probability that they like the product? That's why we use the other totals at the end. Okay, does that make this sense? Okay, yeah.
So whichever one you're given, you use the total from like the far side of that.
Yeah, use the total. That's the total for the bottom.
So
Yeah.
given not liked would mean, like, for example, if it was undecided, it would be 250. Like, given they're undecided, it'd be 250, 30.
Correct. Whatever age group you're asking.
Okay.
Yes. Yep. And it can be asked either direction. So I could say, what's the probability that they're over 50, given that they don't like the product? So it doesn't necessarily have to be the first one and the second one. It's the wording around it. Okay. So it's that given or the assumption that this is a person or those type of words. They say, okay, I already know this piece of information. I want to know something about the other side. Okay. That's the piece that matters. All right, let's look at this one. So out of 300 applicants for the job, 212 are male. Of the male job applicants, 110 have served in the military. So the first question is, what is the probability that a randomly chosen applicant has served in the military, given that he is male? Yeah.
110 over 212.
Right. So the 212 is the male since we're given that. And we want to know if they served in the military. So that's 110. So that's the intersection of the military and the males, 110. And then the male's the bottom. If 152 of the applicants have served in the military, what is the probability that a randomly chosen applicant is male, given that they served in the military? What's the only thing that changes? What was the given piece in this one? Yeah. Or go ahead. Yeah, so the bottom in this case says given that they served in the military. So that's the 152. So that's the military. The top doesn't change. It's still the intersection of military and male, which is 110.
Why is it like that if the 110 portion isn't like anymore? Like, how do I word it? But why are we using that number twice?
Which one? The 110?
The military amount also.
The military amount didn't change.
Oh, okay. I get it.
So in the first problem, before we did the 152, I only told you how many males were in the military. The 152 would include females in the military as well. So technically, I can now ask, what is the probability? So given all the information here, given that the person is female, what is the probability that they served in the military?
42 out of 18.
Almost.
Just given that they're female, right? So it'd be like subtract the overlap. 88.
Why 88?
Because there's 300 applicants and 212 are male.
Right. So you need that extra piece. So remember, so in essence, what did I just find? We found the complementary, right? We have male, so the rest would be listed as female. So,
Total number of people that applied.
right. So in this case, I know I would have 88 females that applied. And out of those, we had 42 that had served in the military. So it's just another way to look at things. All right. All right, next. We talked about two events that are mutually exclusive, which means there is no overlap between them. That's when we're looking at the addition rules. When we're looking at the multiplication rules, the two events would be known as independent. And based on that definition that you see at the top there, basically independent means that one event has no impact on the other event. Okay? So the probability of there is no total. So there's no like given piece there. Because if I say it's given, then you're still at the same exact situation in the first part. Okay, because there's no connection between the two events. Most situations, you're not going to need to know the rule. You're going to be able to look at it and go, okay, yes, there's no connection between these two things, so it doesn't make any difference. So, for example, if we looked at like the last one, those who served in the military and those that lived at the South Pole, like it wouldn't. There's no connection. Like, so those would be independent type events. Again, most of the situations that you're going to see this is in terms of gaming. So, like if you're looking at if I roll a die, the next time I roll a die, the first time I rolled it doesn't have any impact on the second time I rolled it. Those are independent events. So I wouldn't focus too much on this up here. This basically just says what I just said. As long as they are independent, though, we can just multiply those the probabilities together. So that's the big reason why we need to know if they're independent. If they're independent, I can just multiply those events together, and that would tell me the intersection of those events. So I wouldn't worry about this piece here. This is the one that's actually you can use. So as long as they're independent, multiplication gives me that intersection piece. And again, as with everything we've talked about so far, when we actually go through and do a problem, it'll make more sense. All right, so let's look at this one. So a coin is flipped, a die is rolled, and a card is drawn from a standard deck of 52 cards. Find the probability of getting a tail on the coin, a 5 on the die, and a jack of clubs as from the deck of cards. So, first question. Are those three events independent of each other? Does the coin, the die, and the card have any impact on the others? No. So they are independent of each other. So to find the probability, I find the probability of each event and multiply them. So what is the probability of getting a tail on a coin? Odds is 1 in 1. Probability is 1 out of 2. So we're not going to use odds in any of the situations. These are all probabilities. So the probability of getting tails, 1 out of 2. What kind of probability is that? It is 50%, but there was two different types of probabilities we talked about last class. That's theoretical. So when we're looking at these are all theoretical probabilities. Okay, because we did not do any experiments. We're just looking at what should happen. All right, what's the probability of getting a 5 on the die? One-sixth. Yes. Unless they tell you otherwise, assume it is a 6-sided die. The people who make these books do not know games exist that have more than 6 sides on the dice. All right, so we got 1/6. What is the probability of getting a jack of clubs? Yes. That's 1 out of 52. So now all we're going to do is take those 3 and multiply them together. For this type of probabilities, unless the problem specifically asks you for a decimal, it is going to be easier for you to leave them as a fraction. So I will show you, you can use Desmos to do this, which makes your life nice and easy. So in Desmos, you can type the 3 fractions in. It will give it to you as a decimal, but if you click that little button right there next to the decimal, it gives it to you as a nice reduced fraction. Okay? So unless the problem asks you specifically for a decimal and tells you what to round to, leave them as a fraction. Even if it asks you for a decimal, do all your work as fractions until the very end. Okay? Because what will end up happening is, like, if you did 1/52 and changed that to a decimal and used it, you're going to round in the middle and you might get the wrong answer at the end. So fractions will always make your answers come out to be the exact answers all the way through. And then you can always round at the end if you need to. So in this case, this one is 1 out of 624. So that would be the probability of all three of those events happening. Let's do a production one. So I've got 4 different parts. In order for the product to operate properly, each part must be free of defects and work. The probability of the parts being non-defective are given as this. The part A is 0.9, part B is 0.7, part C is 0.8, and part D is 0.9. What is the probability that all 4 parts are defective? So, first question, are all these parts independent of each other? Yes.
No, because it says that they all need to work properly to function.
Okay. So the product has to, when I put all 4 parts together, they all have to work for the product. But is each part independent of the other ones? So if one part's broken, does that automatically mean part C is broken? No. So the parts in that respect are independent of each other? Yes. When I put them together, it becomes one product, and that is what we're trying to find out. But the parts themselves are technically independent of the situation. Yes.
Would they be dependent on each other? For example, like each step built on the previous one directly?
If that was the case and they stated that, then yes, those would be dependent on each other. Because then the one previously would have an impact on the next one up. So, but this case, there are 4 independent parts that are being put together to make the actual item work. Assume there are 4 batteries that are being put in, and if all batteries don't work, if one battery doesn't work, it doesn't work type situation. All right, so what's the probability that all 4 parts are defective? All right, so who's got an answer?
I just had a clarifying question. Are we supposed to put it back into a fraction for them?
No, this one's already a decimal. You can keep it as a decimal.
But I was unsure if I had to make it like 9/10.
No. So if it gives it to you as decimals, use the decimals. That's fine. A lot of times, if it's already a fraction, or we're looking at like the gaming type situations, fractions will make your life a lot easier. But all right, so what do we got?
0.4536.
Okay. Is that what everybody got? Huh? Did anybody get something else? Yes.
I got 0.0006. I'm good.
Okay. Anybody get anything else? Did anybody else get 0.0006? Okay. The 0.0006 is correct. Now, not you yet. Can anybody else tell me why that one's correct? Yes.
Is it because you have to see, like, okay, so what I was doing in my brain, not my brain, my whole sheet.
Yeah.
but I was like, I don't know, seeing the probability of them being defective based on that, like, I don't know how to.
Okay.
Yeah,
Okay.
I think once you do it, yeah, I did it backwards.
Why?
Because I multiplied all of those numbers together instead of subtracting them out of one and then multiplying.
Yeah.
Gotcha.
Yeah.
Okay, so do you want to explain want to go through the steps then?
Yeah, that just shows the probability of being non-defective. We had to find the probability of it being defective. They had to do like 1 minus 0.9, we do 0.1
Yeah.
times 0.3 times 0.2 times 0.1.
Very good. So we needed the what? We needed the complement of them. They gave me non-defective, I wanted defective. Okay. Don't worry, I assume most people are just going to multiply the 4 numbers together. I actually did them both just to make sure I had the right number. If you're multiplying them on your calculator and you get anything like this, anybody know what that is? It is scientific notation. It just means move the decimal that many places. Okay, so that is 0.0006. On your calculator, if you use decimals, that's the way it'll show up. If you use your calculator, sometimes it'll show up with a little e. Same concept. It just tells you how many places you need to move your decimal point. Because the decimal's too small, and they're going to write in scientific notation. So don't freak out about it. Nothing crazy. All right. So A is that one. And for A, we needed to do 1 minus 0.9. All right, so now B. What is the probability that the product does not work?
Would it be like the complement to the 0.453?
Why?
Because it's asking the probability that at least one of them doesn't work. And when I multiplied all of those, I got that number, but I skipped the subtracting step. So if that's the likelihood that it will work, then the inverse would be the likelihood it won't.
Very good. So if I want to, this is a great case of where the complement is extremely important. Because if any one part doesn't work, the whole product doesn't work. So using my battery example, if they have 4 batteries and if one battery doesn't work, the whole product, the thing's not going to turn on. Okay, all 4 of them have to work for the product to turn on and work. So what most of you did when you figured out A, you found the probability that the product will work. Okay, by multiplying those 4 things together. So if I want to find out if the product does not work, I do the complement of that, which I do the 1 minus thing. Otherwise, the only other way to do this would be to actually look at each one independently. So I would have to say, okay, if product A doesn't work, find the probability that the thing is not going to work. If part B doesn't work, find that probability. Part C doesn't work, find that one. Part D doesn't work, find that one. Add those together. But then I also have to say, well, what happens if part A and part B doesn't work? Or I'd have to do every combination of them, which is a lot of work and a lot of steps. But the complement, because it is as simple as if one doesn't work, it doesn't work at all, I can just do the complement to find my answer. So it's 5. Thank you. It'll take me a second to do that one. So that is the probability the product doesn't work. So odds are your product's not working. No. Okay. All right. What is the probability of drawing a king and then a queen from a standard deck of cards without replacement? Yes.
Well,
So,
I don't have the answer yet. I just have some of the steps.
okay, so hold on. Let me ask a question. Are these two events independent of each other? So this piece right here, this part right here, oh, pen. That's the most important statement in this question. Okay, it says without replacement. So if I take a king out of the deck of cards, does my initial conditions change for when I'm taking the queen out? Yes, because now I have less cards. Okay, if it said with replacement, they are independent of each other because the initial conditions did not change. I still have 52 cards. Okay, so what you typically would do in this situation is we're just going to change the criteria. So what is the probability of me drawing a king? 4 out of 52. Now, what is the probability of me drawing a queen without the replacement? 4 out of 51. So in essence, what we just did, my given changes. So the first one, I gave you a deck of cards. That's why it's out of 52. The second one, I gave you a deck of cards minus a king. So that's why it's out of 51. Okay. So your bottom number can change. There is a possibility of even the top number changing too, which we'll do in 1 second for another problem. So in this case, I'm now going to take those two and multiply them. And I get 4 out of 663. What's the probability that I get a pair of kings
Without replacement or with?
without replacement? Because otherwise I wouldn't have the original card to say I have a pair. Yes.
The first one's 4 out of 52 again.
Yep.
The second one is 3 out of 51, right?
Correct. So in this one, that top number has to change as well. Because I have one less king. There's only 3 kings left in the deck. So in this case, it's 1 out of 221.
Wait, how did you get?
What, the 1 out of 221? I typed it into Desmos.
Oh.
Simplified it.
It automatically simplifies it for you. Technically, 4 out of 52 is 1 out of 13. And 3 out of 51 is 1 out of 17.
Oh, so after you simplify them.
Yeah. But that's why I tell you, Desmos simplifies it for you. So, and depending on your calculator, a lot of calculators will do that too for you. So it'll always simplify it for me. That's why I didn't even have the intermediate step, because it just did it for me.
For Hawks, it'll ask for a simple function.
Yes, I know. And actually, a couple of you got that question wrong on the test because you put 3 over 21 instead of 1 over 7. I gave it to you, by the way. Because I knew you had the right answer. It was just you didn't simplify it. So yes, and Hawks at once simplified. Definitely use Desmos to simplify your fractions. Yes.
I assume if we were not to simplify it, the top row would just be, it'd be like what, 12 over.
Whatever 52 times 51 is. There you go.
Okay, and then it was simplified.
And then it was simplified down. Yeah.
Just making sure.
Yes. Yep. All right. Already did that one. Actually, we'll do this one. I like this one. Suppose you draw 2 cards out. What is the probability that you drew the ace of spades and then another spade? Don't say the answer yet. All right. What's the probability that I drew the ace of spades?
52.
1 out of 52. What's the probability that I drew another spade?
12 out of 51.
12 out of 51. Because there's how many spades total in the deck? There are 13. I pulled 1 out, so I've got 12 left. So this one actually also comes out to be 1 over 221. This is why Texas Hold'em is such a popular game, because it's literally all probability. It's completely and utterly probability. They're playing with 1 deck of cards. You can see what's in your hand. You know what's on the table. You can literally figure out the odds of getting what you need to get the hand you want. So it's also why counting in blackjack is so easy to do, because if you can figure out what's out, you can figure out the probability that the card you want is coming out next. All right. 3 more little rules we're going to talk about. The first one is known. So far, everything we've done has been looking at probability. Okay. So what we've done so far, we basically know the bottom number because we're looking at a set of cards or dice, things like that, something that we can figure out. The 3 situations that we're going to talk about now is sometimes how we can figure out that bottom number sometimes. Okay? Because sometimes that's not as easy to come up with. The first one is known as the fundamental accounting principle. So this is the number of ways events can occur. Right? So when you're looking at the fundamental accounting principle, this is basically looking at how many ways or how many phone numbers I can have, for example, or how many different dinners I can get at a restaurant, those type of situations. So yes, no, these are not permutations. We're going to talk about permutations and combinations in a minute. That's why I said there was 3. Fundamental accounting principle, permutations, combinations. Those are the 3. So in this one, you're looking at how many situations can totally happen given each one is independent of the other one. So again, like I said, simple problems sometimes. Phone numbers. Actually, you know what? Let's do license plates. So how many digits are in Connecticut's license plates now? We're not going to assume the customized plates, just the standard plates.
7.
It is 7. So we have a 7-digit plate. The first 2 digits are letters. And then we have 5 digits that are numbers. How many letters can go in the first place?
Is that including the letters that look like numbers? Because I know sometimes they
I don't remember if they eliminated those or not.
'Cause I know like O and 0. Usually on the same.
Yeah, let's eliminate the 0 or the O and the I. Because those can look like other letters. We'll eliminate the O and the I. So how many letters are there? I don't know if they did, but we'll assume that. 24. So there's 26 letters, 24 are left over if I eliminated those two. We can repeat. Can we repeat the letter? Yes, because I've seen AA and BB and things like that. So we can repeat the letter. The last 4 digits or 5 digits are all numbers. How many numbers can there be? How many digits can there be in that first spot? How many different numbers? 10, 0 through 9. Okay, so there's 10 numbers that can go there. 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 So how many license plates can I have? The fundamental accounting principle says just multiply them.
Every single individual number.
Yep.
I got 37.6 million.
24 times 24 times.
And
You got.
57.
Yeah, check your number. Oh, that's what I got. But his was close. Hers was close. So it's like you might have typed the wrong number. 57,600,000.
yeah, that's what I get.
Oh, I thought you said 37.
Oh, no.
That's what it's like. It's like it was close. I'm like, what? Okay. Yes, 57. 57,600,000. That's how many different license plates we can have. That's what the fundamental accounting principle is. All right. So how many license plates can Utah have? I haven't done it. So walk me through the steps.
Well, first, we have the 3 numbers, which means there are 10 possibilities for each slot. Then the 3 letters, which exclude IOQ, which is 23. Altogether, that's 12,007,000.
Sounds about right.
Yeah.
Yeah, that one sounds about right. I didn't do it, so I'm going to assume that is until somebody tells me they got something else. Okay. All right. I actually found out something interesting because every other class up until now, I typically would talk about like Social Security numbers. So Social Security numbers are the same type of situation where you have the last 4 digits are actually randomized, but the first 5 digits, the first 3 and the second 2 are not. However, I actually recently learned that they've changed that. And now the entire Social Security number is a random set of numbers.
When did they change that?
Recently, I guess. So, because it used to be that the first 3 digits told like the states you were born in or the territory, like the area you were born in. And the second 2, I can't remember what they related to something else. So like all of us were like 044, like all, me and my brothers and sisters and everything else, we're all that. And the first 4 or the first 5 are basically the same. It was only the last 4 that changed. Because actually, depending on when you were born, you didn't necessarily get a Social Security number when you were born. I got mine actually when my, I think it was my brother was born. We ended up getting up like I was like 5 or 6 years old before I actually got my Social Security number. So mine and my brothers are almost identical except for the last 4.
I have a twin and hers, ours are basically the same besides the last number.
Yeah. So it's like it's but now, according to what I was reading, they actually randomized the whole thing now. because they were running out of actual combinations. When you restrict that many, you only have 10,000 not possible combinations at that point. So by restricting it, they actually limited the numbers. So by not restricting it, now they have 9 digits. So now you have a billion numbers that they can play with. So,
Probably a good thing for people who are like gamers.
well, yeah, it's like, in all honesty, you need a lot more information than just your social security number to get anything nowadays. So it's like just having your social security number is not going to allow you to get scammed. It used to be that was a big deal. It's not much anymore though. All right. Erase. There we go. Okay. So that is the fundamental accounting principle. Now, the last two. These are the two that most people recognize and remember. Permutations and combinations. So, there's two things here, and it comes up in Hawks, so I kind of have to explain it now, because I didn't think it did come up in Hawks, but then we found it does. So this symbol right here, that is known as a factorial. Okay, that little exclamation point means a factorial. So 5 factorial means 5 times 4 times 3 times 2 times 1. So all a factorial does is it takes that number and multiplies it by all the numbers all the way down to the final number. Yes. Yes, just integers. Now, I will tell you that Desmos will do it for you. Okay? Just put the exclamation point. Like, for example, here's 56 factorial. It'll do it for you. So don't sit there and stress out about it. If Hawks asks you to use it, there is a couple situations, and we'll talk about it a little bit later, that the formula, you do need it. You will not use it for permutations or combinations, because in Hawks, they have those 2 buttons right there for you. Actually, most calculators do, except I don't think your like standard calculator on your phone does. I don't believe it has those. No, they do not. So, but most scientific calculators, if you bought any, or like the TI calculators or your scientific, they will have an NPR button or NCR button on the calculator that you can use. So you are not going to have to use the formula like this here with the exclamation points and everything else in them. You're just going to actually use that. Okay. Permutation and combinations, they look very similar. The problems will be very similar. The distinct difference is, does order matter? Okay. So for permutations, order matters. All right. So in a permutation, order matters. So if we're looking at a phone number, does order matter in a phone number? Yes. Okay. I can't switch the last 2 digits and call you still. So order matters. That's what it means by order matters. It's that list of things has to be in a very specific order for it to work. Okay. And when we're looking at these, we're not just talking about numbers. It can be anything. It could be letters. It could be words. It could be, like I said, dinners. It could be CDs. It could be whatever you want. Okay. It does not necessarily have to be a list of numbers. It has to be numerical. We have to be able to count it to be able to come up with things, but we don't need an actual list of numbers to do this. So permutation, order matters. I was like, where's the problem? All right, so 7 sprinters have advanced to the final heat of the track meet. So we have 7 runners. how many different ways can they finish first, second, and third? So, does order matter? Yes, because they're specifically placing them. If I said, how many ways can I have a podium? Order doesn't matter, because in that case, I wasn't separating them out first, second, and third. But since I'm separating out first, second, and third, order does matter in this situation. So we are going to use a permutation. So this is NPR. The N is the number of values I have. The R is how many I'm choosing. So in this situation, I have 7P3. There's two different ways this can be put into your calculator. Some calculators, you actually put it in just like this, as 7PR. Some calculators will be listed, it'll look like this. It'll be NR and then 7,3, which is what Hawks does. I mean, not Hawks, Desmos. So in Desmos, you would click your function. So it's typically on this screen. You click functions, and then NPR is right there. So when you hit it, it's going to give you the two parentheses. Just put 7,3. And then that's your answer. So there's 210 combinations. Yes. So on whatever calculator you're planning on using, do this and get that number. So you know how to do this when you go home to do your homework and everything else. If you can't figure it out, ask, and I will show you. All right. Permutations is literally that simple. That's it. Okay. These are not overly complicated things. Now, if I was saying, what's the probability that I would come in third? Like, you can now figure out, okay, I got 210 combinations. There's 7, like, we can now do a probability. This is going to help us get those bottom numbers to do some probability problems. All right. Distinguishable permutations is a special situation. And this is a situation where you will need to use the exclamation points. So in the last problem we had 7 different individuals running. They were all different. If I wanted to figure out how many different ways I can organize the letters in Mississippi, for example, is every letter independent of each other? Is every letter different? No. So if I took 2 S's and swapped them, it doesn't make a difference, right? So that's where the distinguishable permutations come in. In this situation, we need to put down how many of each value exists. So, this is the one formula you're probably going to actually need to write down at some point and mark, because it's a very specific situation. So, for example, in Mississippi, how many letters are in the word Mississippi? 11. So I have 11 factorial on the top. How many M's? How many I's? Yep. How many S's? How many P's? These 4 numbers down here should add up to that. If they don't, you screwed up. Now, you are not doing this out by hand. You're going to go to Desmos or your scientific calculator, whatever calculator you're going to use, and you're going to type it in. If you're doing a fraction on Desmos, what I would suggest always doing, put the fraction button first. Okay? So hit the slash key as the division key to get that fraction there first. We do 11 factorial on top, 1 factorial, 4 factorial, 4 factorial, 2 factorial. And then that's my answer. Again, do not try to do this out by hand. There are ways to do it. And if I really wanted to teach you how to do the factorial and everything else out, I could and you could do it, but you're never going to do it after this class. So there's no point in me going through and teaching you how to do out factorials by hand. So I got 34,650. And basically what that does is it allows me to choose basically all of them without having to make any difference. So if, for example, that I wasn't choosing, like all the letters were different, I would have had 11 times 10 times 9 times all the way down. Basically, I would have had 11 factorial. So I would have had 39,916,800 different ways I could put those letters together. Okay. So your question earlier was, isn't that a permutation? The difference between the permutation and the counting principle is, in the counting principle, I'm taking all of them. So I have 11 and I'm choosing 11 of them. That's the difference. In permutations, I'm picking a certain subset of them. Yeah, basically, yeah. It's like I'm taking, like, out of those runners, I'm taking, how many different ways can I pick 3 of them? That's where we're looking at the permutations. Okay. The reason this is here is because I know there's a problem at Hawks that specifically asks for this. So you will see this when you do section 6.4. Combinations. Order doesn't matter. Permutation order matters. Combinations order does not matter. That is actually the only difference. And it's a C instead of a P. So it's NCR for combinations. Yes. Ignore the formula. Or formula. I know. I don't know why they used a K. Because I believe in this one they used an R. Oh no, they used a K there too. There's certain things in Hawks that they do differently, and I don't know why. Everything uses NCR and NPR. Every calculator has an R on it. So I don't know why they used a K. I think somebody just wanted to be different. All right, so combinations, order does not matter. So I will tell you the hardest part of doing these is going to be determining that piece. Because they're not going to say, use combinations on this or use permutations on this. They're going to give you a problem and you have to determine which one you're going to use. So, in South Carolina's lottery, you're picking 5 different numbers from 1 to 38 inclusively. Very important in a second. If the numbers selected match the player's numbers in any order, the player wins. So, what is the total number of winning combinations? So, does order matter? And if you ever play the lottery, order doesn't matter. The balls can come out in any order you want, right? And on your ticket, they're always in numerical order, except for the play 3 and the play 4. Those are a little different. But your typical, like, big lotteries, your orders are always in numerical order on your tickets. But the orders come out, whatever ball comes out at any point, it doesn't make a difference. So order does not matter. So we're going to use combinations in this situation. So we're going to use NCR. So how many numbers am I choosing from? Why is it 39 and not 38? Correct. This goes back to the whole class width type of thing we were talking about. Like 0 to 9 is not 9 numbers, it's 10 numbers because we're including the 0. Same thing here. 1 to 38, there's 39 numbers we are choosing from. How many numbers do I want to pick? Picking 5. So how many different ways can I, how many different combinations or tickets can I buy? Yes,
Oh, sorry.
that's okay. How many? Going once, going twice. Good. What's the probability of winning? Yes. Yes. Because only one of those is coming out as a winner, right? So here's actually a very interesting thing about this. So it actually happened in Massachusetts a couple times, actually. Massachusetts screwed this up multiple times. So their lottery was very similar to like this. And if you know anything about Massachusetts, they have some very like prestigious colleges, including MIT and Harvard and stuff like that. Well, a group of students from MIT decided that they were going to win the lottery. So they bought every single ticket. They figured out a way to go to all the different stores and buy every single possible number that there was. And they did this because the lottery was like $10 million and there was only about 500,000 tickets that they had to buy. So they bought them all and they won. Yes.
How much do you think that cost a ticket?
500,000 something dollars.
All right.
They're $1 each.
Yeah. At that point they were. And they won $10 million.
How many
Pretty
people
good
did they split it
profit.
between?
I think it was like a group of like 5 or 6 of them that did it. So Massachusetts obviously did not like this and they changed the rules. So they changed it a couple of different ways. They actually added numbers to make the odds a lot higher, which is typically what you see in like the Powerball and the Mega Millions, stuff like that. When it doesn't keep going up higher enough, they just add a number to make it bigger and bigger jackpots. That's why all of a sudden we're starting to get $1 billion jackpots now, because the odds of winning is like 1 in like 200 and something million. It's ridiculous. The other thing they did is they actually put limits on the number of tickets that each place could sell and that you could buy. So you can only buy 100 tickets at a time now, which prevented anybody from being able to go do this. So what they basically did was they went into a few different stores and they basically monopolized the machine the entire day. And they had all the things already printed out in tickets. So they just kept running them through the machines. 21? 21 is the one where they gamed the casinos in Vegas with counting blackjack.
Oh, Bryan Cranston, but it's just like you're saying, like they'd all pull together.
Yeah.
and go,
Yeah. So it's these type of situations that, again, it's knowing the odds, it's knowing the probability, it's knowing how to actually manipulate them to work in your favor. So the nice thing is they won and they made their money, but nobody else is going to be able to do that again. All right. There we go. A DJ needs to select 6 songs from a CD containing 12 songs to compose an event's musical lineup. How many different musical lineups are possible? Now we're going back into that whole, does it matter or not? Does order matter? If I play blank space before Cowboy, what is it, Cowboy Anthem? Does it matter if I play the other one first? Does it make a difference?
It depends on who you ask, I guess.
Okay. But they're all gonna be played, right? So I'm gonna say order doesn't matter. Actually, wait, let me rephrase this. Yes, order doesn't matter, because it doesn't make a difference which song's played. 6 songs will be played out of the 12. So since order doesn't matter, we're gonna use what? Combinations. Okay, so that's the piece you have to decide. They will be a lot easier to decide later on. As long as Freebird's not played, it's all good. All right, so we get 924 different ways that I can.
Yes, and then against Freebird.
I'm the one who always yells Freebird just to annoy people. It was funny. I was in Pocono at the race, and there was a Leonard Skinner tribute band that was playing. And everybody wanted to play Freebird, because obviously it's like play Freebird. They didn't play it till the very end. Yeah. So it's like, nope, we're not playing it. Nope, we're not playing it. It's like, played it at the very end. How many 5-card hands can be dealt from a deck of 52 cards? Oh, I've been here too. The screen goes out after 90 minutes. Combination or permutation?
Is it permutation? Because once you like take a card out, it's
No. So combinations and permutations takes that into account.
oh, okay. In that case, it's-
So this is combinations. It doesn't matter which order the cards are dealt in. It's still a 5-card hand, right?
Yeah.
Okay. So we've got 202,598,960. 52 cards, choosing 5. Anybody know what a royal flush is?
so you're asking me to
Yes,
define it?
what's
It's,
it?
they're all the same suit, and it's ace through 10, right?
Yes.
So like it would be, if it's like all hearts, it would be an ace of hearts. And
Yeah.
king of hearts, with the-
All right. So here's the question. Do you have better odds of getting a royal flush or winning the South Carolina lottery? Figure it out. You know all the information needed to do it.
so it says odd.
No, probability. It's not odds.
Wait, how many cards are there in the flash?
5. It's one hand. So basically the question is, how many different royal flushes can I get? There's 4 different royal flushes I can get out of that many possible hands. And this was the probability of winning the lottery. Remember, one out of the. So, do you have a better chance of getting a royal flush or winning the South Carolina lottery?
There's so many schools. Sorry.
You have a better chance of winning the South Carolina lottery. Yes, both of them are extremely unlikely, but you have a better chance of winning the South Carolina lottery. So as you can see, when you're starting to look at probability, we're using the NCR, the combinations, the permutations, the counting theory to find the bottom number, and then we can use that to figure out a probability situation. Since there's 4 different royal flushes, we do 4 divided by the number of cans, and the lottery was 1 over that. All right, I don't want to do that one. All right, we are done.